We're going to dive into the world of functions and derivatives without math. So if you're not a fan of all those derivative equations, this might be the time for you because we're going to draw pretty pictures. We're sketching between a function and a derivative or backwards from a derivative to its function. The homework assignment that goes with this is going to be some problems from the AP Classroom website. Let's get rolling. Here we have a gentle little parabola just sitting there minding its own business. If I had this, I could go ahead and take the derivative and say that's 2x minus 4. Now I realize I just said that we're not going to be doing any equations and formulas, so I guess I lied to you, but believe me, there won't be much of them. Well, if I take a look at this picture and this picture, I'm going to start being able to see connections between this as an original function and this as a derivative, just like your eyeballs see function and derivative. So let's take a look at why that would be the case. As I look at this graph up here, I'm going to shade the section of this graph that has a negative slope. Well, if it has a negative slope, that means its derivative should be in negative territory, or it should have negative y values. Negative slope, derivative in negative territory. Then if I look at this part right here, these are all positive slopes, and my derivative is in positive territory. Okay, that's pretty loosey-goosey. We're not applying any numbers to that, so let's start applying numbers, and I'm just going to make them up so they may not work perfectly with these equations. But like, say, right here, I might say this slope is negative 5. Well, if the slope at that spot is negative 5, that means the derivative value at that same x location should be negative 5. And, okay, ignore my scaling here. We'll say that y value is down there at negative 5. We can get more accurate. For example, what's the slope right there? Well, the slope of that function, it has a horizontal tangent line right there. So the slope at that spot is 0. And take a look at this. The derivative value at that spot is also 0. If I look on a parabola just to the left of that spot, my slope would be really tiny. It's still negative because a parabola still has a negative tangent line, negatively sloped tangent line, but maybe it's a slope of negative 1/2. Well, that same location just left of that spot, if you notice, the derivative has a y value that is just barely negative. So if I continue to do this, say right here, the slope of the tangent might be 1, and at that same spot, the y value on the derivative might be 1. So what you're seeing is the slope of that tangent line at any spot you pick on that graph should be reflected in the y value on your derivative graph. Basically, the relationship can be summed up this way. The slope of f of x is the same as the y value of f prime of x if we're looking at the same situation. So you could get literal numbers and make that work, or you could just be a little loosey-goosey. My slope is very negative right here, but it's getting less and less negative until the slope is 0. My y value is very negative, but my y values are getting less and less negative until they're 0. My slope is barely positive, but gets more and more positive. My y values are positive, and they're getting more and more positive. All right, so that's a little bit for your brain to digest in the beginning. I'm going to walk you through, I think, 2 other examples, maybe 3. Probably going to go a little faster, but please stick around to the end of the instructional video because I'm going to then apply this to a situation where we're going to use the rate of change graph to look at the function graph that represents something real in the world. And if you're really understanding this, you could fast forward to that part at the end. Here's one that I've already put down the original function and its derivative. And to go from here to here, that's one of the easiest derivatives you could get. But let's think of it in picture form. As I move along this line, the slope is always 3. So the slope of my function is the same as the y value of my derivative. If the slope is always 3, the derivative would always have a y value of 3. And as you're starting to see this, realize that they could give you a y prime and you'd have to swim back upstream like a salmon going against the current and come up with the y that gave birth to that. All right, let's take a look at another one. Ooh, all of a sudden it's getting a little bit funkier. And there's a trap in this one, but we'll take a look. Here's my original function, probably was a piecewise function, and we're going to sketch a derivative. Well, I'm going to kind of talk to myself as I work this out. I say, hey, in this stretch, the slope is never changing, and it's always positive, and it is, I don't know, I'm just going to estimate a slope of 2. So since we don't have any real numbers to hold ourselves to, we can estimate. So along this whole stretch, if the slope is 2, that means the y value of my derivative should also be 2 along that whole stretch. So I'm going to mark that spot and say my derivative has a value of 2 up until that spot. Now I'm going to put a mysterious open circle here. I hope you know why, but there's a chance you don't know why. Now I'm looking at this part, and now this one's a lot tougher. At this point, the slope is negative. At this point, the slope is positive. At this point, the slope is 0. So that tells me my derivative goes from negative to 0 to positive. That means the y values of this have to go from negative to 0 to positive. In fact, if that's when my slope is 0, horizontal tangent, famous like Johnny Cash, I'm going to put a mark on here. My derivative is going to have to take on a value of 0 at that spot. Horizontal tangents and y values of 0 on the derivative graph, they go hand in hand. Now if the slope is negative, but notice it's getting less and less negative, that means my y values have to be negative and getting less and less negative. That's a pretty steep slope, more than -2. So I'm going to say, let's say it starts out at say -6. Okay, I went off the graph, but that's okay. I'll do it. Okay, so -6. I'm going to put the open circle there, and my slope is getting less and less negative until it's 0. My y values get less and less negative until they're 0. This is kind of a symmetrical mirror image on the other side. Slightly positive slope, growing more and more positive. The y values of my derivative are positive, growing more and more positive. So 2 major facets of this derivative graph. One you should always pay attention to, horizontal tangent on original function, derivative value of 0. Those are good anchor points to kind of guide your thinking. And then why these open circles? Here's why. Long time ago, when you were young, you learned that a corner point on a graph is an undefined derivative spot. Technically, the left-hand derivative and the right-hand derivative, or the left-hand slope and the right-hand slope, are not equal to each other. Well, if the derivative is undefined at that location, then the derivative graph should be undefined at that location. Corner point, undefined derivative, derivative graph, undefined at that spot. Side note, I've jumped back to this first example. I didn't make a big deal of it then because there was a lot going on, but look at this. Horizontal tangent, that means slope is 0. Derivative graph, value of 0. All right, we're going to do, before we get to the applied example, one more example. I have a derivative here, and we're going to create the actual original graph, f of x. It might be worth your time to pause the video and try to create that on your own. That's up to you. I'm going to pause the video and create it on my own and then explain what the heck I did. Okay, that may or may not be what you came up with, but let's take a look. My derivative, the y values of this thing have to be reflected in the slope of that thing. I went ahead and wrote that out. You might want to keep that handy for you if this is tough on your brain. Well, my y values on my derivative were getting smaller and smaller but positive until they got to 0. That means I needed a positive slope over that interval until the slope was 0. Good anchor point, horizontal tangent, derivative value of 0, they should match up. Now my slope started to get slightly negative, and that's because my derivative graph where I started, it was negative y values getting more and more negative, negative slope getting more and more negative. At this time, now all of a sudden all my y values on my derivative stayed constantly at, say, -2, so the slope of my graph should stay constantly at -2. One final point, this corner point might concern you, and you might think we need some sort of open circle on my f of x, some sort of open circle on my f of x graph, but that's not the case. Remember, this would have an undefined derivative, so if we were to go forward and do an f double prime graph, the derivative of f prime, then we would have an undefined location on that graph. But going back upstream, not the case. All right, well, thank you for sticking around so long. I'm going to now go through this applied example to a deer population. All right, the title of this graph would be Deer Population Rate of Change. And that is the big deal right there. This is not a graph of the deer population. It's the graph of the rate of change. In fact, you would probably know it can't be the deer population because you can't have negative number of deer. So once again, we're loosey-goosey, no actual numbers to work with. But almost every one of these questions that you see here is a trap. And it's a trap because your brain is not used to looking at a rate of change graph. Your brain is looking at, say, a deer population graph. So there's going to be a big jump here. Now, some of these questions have more than one answer. When is the deer population decreasing? You're tempted to say F, but remember, decreasing population graph means a population graph with a negative slope. So you could answer either A or B. A is debatable because it's an endpoint, but B for sure. The deer population is decreasing because the derivative, this is really a derivative graph, population prime we'll say, the derivative had a negative y value, that means the population would have a negative slope. In fact, let me show you. I took the time to graph this population. Here is the derivative. When the derivative has a value of 0, my population graph would have a horizontal tangent, slope of 0. Derivative in negative territory, population decreasing. Derivative in positive territory, population increasing. So I'll show you this from time to time as we answer these remaining questions. When is the deer population growing most rapidly? You're tempted to say D because D is a very steep location on this graph, but because this is a rate of change graph, the greatest rate of change occurs at E. At E, my derivative is the greatest, which means the deer population would be growing at the greatest rate. Greatest Y value on the derivative, steepest spot on the graph. When did the deer population switch from declining to growing? At C. Because the derivative went from a negative y value, negative slope on my real graph, to a positive y value, positive slope on my graph. Name a spot where the deer population is increasing. You might be tempted to say B because we're at a positive slope there, but remember, this is the derivative graph, So we would have to say either D, E, F, and G is debatable. That's an endpoint, so that bugs people, but it really is a valid answer. Most people would be tricked into not saying F because they see a negative slope. Same trap. This is a derivative graph. When is the deer population at its minimum? All right, so the minimum, there's other ways to do this, and when we watch this video, I'm not sure if we've done curve sketching yet, so I'm going to ignore that for a moment. And if I had taken the time to graph that, the minimum occurs at C. If we've already done this subject called curve sketching, you would say because P prime switches from negative to positive. If this doesn't make any sense to you, that means we just haven't done curve sketching yet, so no big deal, because you can still reason that out by graphing it. And when is the deer population at a maximum? Well, if the deer population was going downhill for a while and then it increased for quite a while longer and at a greater rate, it's going to end the timeline at its highest population value, like that. All right, this was a long haul. I thank you for hanging in there. This is definitely an unusual way to think about derivatives in the original function. So thank you. We'll catch you later. Bye.